Hello everyone, my name is Kwangsung from University of Minnesota, and today I'm going to talk about our work TripS automated multi-tier data placement in a geo-distributed cloud environment. This work has been done by me and my two advisors, Professor Abhishek and Professor John. It is an honor for me to give a talk in front of you at Systor 2017. Let me start with our motivations. So today, there are so many cloud providers available. For example, Amazon AWS, Google Cloud, and Microsoft Azure, and IBM, and so on. And most cloud providers have multiple data centers on the multiple locations. And the recent user of the internet services are also distributed. And to serve their users, many internet service providers use such cloud provider resources in the multiple data centers without having their own data centers. So for example, Airbnb and Uber and Netflix use AWS to serve their users without having their own data centers. Although typically the internet applications replicate data to the multiple locations for data availability and then reduce the user perceived latencies. So in this scenario, in this environment, the one question should be arise is where are the best locations for storing data? So answering this question is not easy task. This is because the application developer should consider so many their goals. So all of this goal is the application developer should consider to achieve. And then considering all of this, the goal is bring a lot of complexities. So this is not easy to answer. To relax this burden, the many previous work has been proposed. So all of this work try to find the optimized data placement instead of the software developers. However, all of this work only focuses on a data placement with the multiple data center locations. However, recently many cloud providers starting offering the multiple storage tiers within a single data centers. So they provide SSD, hard disk, memory, and object storage and archival storage and so on. And then each storage tier has a different characteristic. So they have a different performance and then pricing and the durability and data availability. So now the choosing appropriate data storage tiers become very important because it can significantly affect the overall data placement, optimized data placement. So in this work, we argue that such data placement system should consider not only the data center locations, but also the storage tiers for the optimized data placement. However, such systems have several challenges they have to overcome. The first one is the many options. So as mentioned, each cloud provider has so many data centers on the multiple locations. So all of these data centers are available to the software developers. And then this figure shows that the number of the data centers for each locations. For example, there are more than 300 data centers, even US East area only. So in this figure shows that there are 8 available data centers in Israel. So software development, such systems should consider so many data centers, especially within a specific area, so for a single location. And then as also mentioned, each cloud provider is now starting to offer so many different types of storage tiers. For example, Amazon AWS provide 9 different types of the persistent storage. And then they also provide even more different types of storage, such as file systems and database and the cache or something like that. And other cloud providers also provide similar number of the storage tiers. So if we combine the data center, number of the data centers and the number of storage tiers, there are so many different types of the combinations available. So this should be the challenge to be overcome for the optimized data placement. The next challenge we want to address in this work is the dynamics from the cloud environment. The dynamics can come from the infrastructure of the cloud providers. The reason is because their resources are shared by multiple users. That's why typically the cloud providers do not guarantee constant performance over the time. So this kind of the dynamics can happen because of the transient data center failures or network failures or the burst access pattern or overloaded nodes. There are so many reasons. And then the dynamics can come from the application itself, because now the application needs to serve the users geo-distributed, and then the user can move around, and then their access pattern can also keep changing. I mean, some data popularity can change over the time. So any of this dynamic can hurt the application desirable. So application developers may want to achieve their desirable even at the presence of such dynamics. So in this work, our goal is to finding optimized data placement by exploring both the data center locations and the multiple storage tiers. And then we want to help applications to handle the dynamic to achieve their desirable. This is our two goals in this work. So far, I have discussed about our motivation and goal, and then now let's talk about our systems called TripS, storage switching systems. We designed the TripS as a lightweight data placement decision system. So the TripS can run on top of any applications or underlying the systems that require to find optimized data placement in a multiple cloud environment. So as we for achieve our goal, we consider TripS consider both data center locations and then storage tiers to further optimize the data placement. And then, of course, we consider to help applications handle the dynamic to achieve their desired goal. In this work, we assume that the TripS is running on top of the Geo-Distributed storage systems we call the GDSS. And then GDSS server is running on multiple data centers, even across the multiple cloud, different cloud providers. So, and then we also assume that each cloud, each GDSS server try to exploit multiple storage tiers for each single locations. And then we also assume that applications are running on the GDSS. So in this work, each application don't have a chance to communicate with the TripS for the data placement, but only GDSS, the storage system, will communicate with the TripS for simplicity. So application now can connect with any available GDSS server, maybe possibly the closest one, and then they only need to know how to send a request to the GDSS to send a request to GDSS. This figure shows that how the TripS work with the underlying GDSS. So now the user needs to know about the GDSS user interfaces. And the TripS can run on separated as a standard or can be included in the GDSS. It's up to the how we can implement it. So now the application needs to send some input, can send a request over some the TripS input, such as application goal. And then GDSS is responsible to send some aggregate some monitoring information for the optimized data placement. Whenever the GDSS need to reevaluate data placement, it needs to send aggregate all input and then send it to the TripS, and then TripS find the optimized data placement and then return the result to the GDSS. Now GDSS have the place where they have to put the data for the optimized data placement and then achieve the application goal. So because in this work we consider data center locations and storage tiers, we introduce new notion of the locale, which is a tuple include the data center locations and then storage tiers as an element. So in this figure, this tuple indicated SSD on the US East data centers. So in this figure, there are 9 locale available, 9 locale, 3 locale from each location. So with a given system model and the notion of locale, we define the data placement problems as determining the set of locale to store data. So each, the subset of the locale will satisfy the all application goal, and then of course it will satisfy some constraint determined by applications or underlying systems. So for the optimized data placement, the TripS require different types of input. The first one is application desire goal, and then cost information. Because in this work, we will try to minimize the overall cost. I will mention later a little bit. And then it requires also latency information for the storage and the network latency between data centers. It also requires some workload information from the applications or users. And then this is the more details available in the paper. And then the TripS, once the TripS acquire the input from the system, it model and solve the data placement problems as a MILP, mixed integer linear problem. So our objective function is to minimize total cost. The total cost can be estimated with some of all these different types of costs. And then each cost can be calculated with these equations, and then I won't go in detail. So please take a look at the paper more in detail. And then with a given input, the TripS determine the data placement, and then finally you may find some data placement, such as the TripS may determine that hard disk on the US East or object storage on Asia Southeast. So now the GDSS can use these two locale for storing data to serve and then to serve the application request. So far, I have discussed about how TripS work with GDSS and then what is the input for the TripS for the data optimized data placement. Now let's talk about how the TripS help applications handle the dynamics to help them achieve their desired goal. So far, many previous work focused on the long-term dynamics, which happen very slowly. I mean, for example, the manual access patterns or the user locations. This kind of dynamics happen very slowly. So these dynamics happen from hours or weeks. So that's why the lazily evaluating data placement is enough, and then that's why many previous work use it this way. So likewise, like other systems, TripS also re-evaluate data placement to handle this kind of dynamics. And then, however, the short-term dynamics is more happen frequently in the cloud environment. This is because their resources are shared. So that's why the cloud providers does not guarantee constant performance. And then this kind of dynamics can happen because of the burst patterns or failures or overload. So this kind of dynamics may happen from the second or several tenths of a minute. So however, to handle this kind of short-term dynamics, the evaluating data placement is very expensive because as the meaning of the short term, the dynamics may disappear after some amount of time, and then the evaluating data placement itself is very expensive because it needs to aggregate all information to the centralized locations, and then it requires some CPU or some time to evaluate it. So to handle this kind of dynamics, we try to handle this dynamics more proactively with a new notion of Target Locale List, TLL, which I will give more in detail next slide. So TLL, Target Locale List, we call the TLL, is the list of locale which is satisfying the SLA goal from each location. So let me give you some example. So application may want to set as parameter equal 1. As a parameter is actually determining the set of the number of locale from each location can have within SLA. So let's say the application determine the as parameter 1, and then for the simplicity, let's say this one is A and B, C, and data set C. So and then we let's assume that the data TripS use the hard disk on data set A and the object storage in the data set C. Then, as you can see, each location can have at least one locale can access within SLA. So this location can access to this locale to avoid any SLA violations. And then this locale locally can access without any SLA violations. However, the problem is the dynamics. So if the dynamics happen, I mean the network is failed or some significant delay happens, the application running on this place have to retrieve data from here. However, because of the wide area network and then slower performance of the object storage, it may see some of the SLA violations. To avoid this scenario, to avoid this SLA violations, application may want to set the as parameter equal 2, which means each location now have at least 2 locale within SLA. So this is a new constraint, and then with the given new constraint, the TripS will re-evaluate data placement. Now the TripS decide to use the SSD on data center A, and then hard disk on C. So now each data center has 2 locale within SLA. They can access within SLA without any SLA violations. So in this scenario, the application running on the data center B now have 2 options. So even if the dynamics happen from the network or failure happen, you can still retrieve the data from the hard disk on the data center C without any SLA violations. Of course, this will bring some more extra cost because this maybe the Asia data center on Asia is charging more expensive the network cost. However, with some extra cost, application now have some trade-off cost for the performance. By having multiple locations, the TripS can provide some trade-off for the application for trading off the cost for the performance. So far, I have discussed about how TripS have handled the short-term dynamics, and then let's take a look at the experimental evaluations. So for the evaluation, we just run the TripS on top of the Wiera, our previous multiple cloud environmental storage systems as a GDSS, and then we use the Amazon data centers, and then we use 3 storage tiers, EBS, SSD and hard disk and object storage, S3. And through the evaluations, we want to illustrate the TripS find optimized data placement, and then TripS can help applications handle the dynamics and then help them achieve their desired goal. For the first experiment, we want to show that how the TripS choose the data placement with a given the workload. So to show this, we just use two synthetic workloads. The first workload is a latency-sensitive web applications which use small size of data, and then data is the frequently accessed, and then the application desired goal is somewhat lower. And then for the second workload, we try to simulate the data analytic applications which use big size of data, and then data is less frequently accessed, and then the desired latency is somewhat higher. And then for the comparison purpose, we compare this result to the span store, emulated span store. So span store is the only purpose on the data set location, but not storage tiers. So we emulated span store by allowing TripS to use only single storage tiers on a single data center. So TripS used any combination of storage tiers for each data centers, and then the emulated span store only used only single tiers for each data centers. We normalized all the results to the TripS case, and then as you can see, S3 is you can see the many cost implications because of S3 charge for the request. So even the S3 provide the cheaper storage cost because S3 charge for request, and then workload 1 is the data is frequently accessed, and that's why the S3's cost is very high. In this case, EBS is better choice because EBS don't charge for the request. For the second workload, as you can, we also normalize the TripS case, and then in this case, because now the data size is big and the storage cost is become more important. That's why the TripS always choose S3 for the second workload. And then now EBS has a more expensive cost because the EBS has a more expensive storage cost. As you can see, in the both workloads, TripS choose to optimize data placement with minimize the overall cost. The second, the experiment is to show how to handle the dynamics. So to show this, we use the 5 data centers on North America region, and then each location simulated client keeps sending the request with this workload. I mean the really intensive with a small size, and then the application want to very somewhat lower latencies. To see the comparison, we vary the edge parameters to show how they can help application achieve desired goal. And then this graph shows that the user perceived the latency is running on US list. So the application desired goal is 80 milliseconds. So the application running on US list can access the data very fast because it can access the local storage. However, if the dynamics happen, some delay happen, there's nothing they can do. They just see somewhat the higher latencies. But this is fine because the application is at 80 milliseconds, and then the latency is still below than 80. However, the dynamics may cause SLA violation. In the case, application should see this SLA violation because the LC parameter is set only one. However, the application set the LC parameter 2, then the application have a 2 choice. So if the dynamics happen and they detect, the application can access the US East 2 SSD to avoid this SLA violation. Of course, again, this will cause some extra cost. However, now application can avoid SLA violations. So this table shows that as long as the S parameters increased, the overall total cost also increased. However, by paying this amount of the extra cost, the application have more options to avoid such the dynamics happen the very short time, small amount of time. And then the TripS also can use this somewhat faster storage tiers to satisfy these S parameters, or increasing the number of replica to satisfy these S parameters. The last experiment was to only show that the real application can get the benefit from the TripS, and then we use the Retwis, which is a Twitter-like application, and then we set the get SLA 80 milliseconds, and then SLA is 200 milliseconds, and then as you can see from each locations, application can achieve their desired goal, which is much below than SLA goal of the applications. So far, I have discussed about the TripS, and then TripS, I show that the TripS find the optimized data placement with the consideration of both data center location and storage tiers. with a minimized cost, and then I show that the TripS can help applications achieve their desired goal even at the presence of dynamics. This is all I have today, so I will be happy to have your question if you have. Thank you.
Any questions? Yes.
Thank you for the talk. How is this different from distributed facility location problem? What is the connection to distributed facility location problem?
I don't understand exactly. So, what do you mean by facility?
The distributed facility location problem?
I mean, you mean the resource?
Where to put the facilities?
Facilities location.
This is an operations research problem. It's kind of a classical problem. Facility location.
Oh.
Facility location.
I don't. Yeah. So I don't think that this is different from the previous work. I mean, we just try to say that many previous work focus on some that don't care about the storage tier, but only locations of data centers for the optimized data placement. And then there are many previous work. And then we add some more constraint as a new option for storage tiers within a single data centers. So now the data can be stored at multiple locations and multiple storage tiers. So we just give some new options as a data placement.
Any other questions? Maybe I have a short one. You didn't talk about the computation time it takes to find your optimized.
Oh, sure, yeah, yeah.
Right. So how long does it take for your scenario?
Yeah.
And how do you think it would evolve if you then increase the number of?
Sure, yes. Because as I mentioned, the evaluating data placement is very expensive and takes some time. So in our work, if we use the 8 data centers and then 3 storage tiers, it takes about a second to find the optimized data placement. However, if we increase the number of the data centers to 10, more than 10, it takes about more than 10 seconds. So it's increased, not linear, but exponentially increased. So this is a separate problem we need to address. So to minimize the number of the evaluated data placement is also very important, and then it's good for the next future work to handle this.
Thank you. So let's thank the speaker again.